Welcome back. Today we're going to take a look at the second case study in our 208 class. Now here, what you see, it's this injector cap with controlled brake. And what it is, the military has commissioned development of a rapid deployment anti-chemical/biological agent injection unit. It's kind of like an EpiPen, basically. All right. Now, the primary development companies have a difficulty with field tests that indicate the breakable cap is detaching and clogging the injector nozzle. That is this part right here. So basically, as it twists, like imagine if you were to try and twist that with just like twisting a knob on a stove. All right, and you want to rotate it just like you see here to enable this to break off, and then fluid could get through this little area here. And this has a cap on it, just like an injector needle here. Actually, it is a needle, and it lets the fluid flow through. Now what was happening is this little cap here breaks off, and then it clogs inside this unit, clogging the orifice, so the fluids can't flow through, and you can't have that out in the field, all right? So this is actually based off of a real case study. I changed the parts and the application a bit, so it's different, but it was one that I ran through, and it was really cool, the solution we came up with. All right, so anyhow, let's get started. First of all, make sure you go to your manufacturing 2208. Oh, by the way, if you're not there, you go to home, which is Vertani1.com, go to Bracia, Vertani2, and find manufacturing 2208. Now from here, first of all, download the case study if you don't have one already. And most of you already have one that has your name on it, and you've hopefully turned it in already. But basically, here's the template you could use. I would recommend downloading it. Now, if you don't have Microsoft Word and you can't afford it, remember there's LibreOffice. Just Google it and you could download LibreOffice, and that's free. But now that I have this downloaded, I'm going to click on Open in Word, Enable Editing. All right, and now let's go back here to the 2208, and you'll see Lab 2. That's the files that we want, so go ahead and click on Lab 2, hit Download, and you'll see the injector. Just click on that, and right-click on that folder, and cut it out. And I'm going to just drop it on my desktop. Right-click on the desktop, and paste. And now, if we go to the desktop, we'll see the injector, and here are all the parts. Now, I give you more parts than you really need. Part of doing case studies is to understand what you need and what you don't need. And you don't want to do more work than you have to, all right? Especially when you're doing analysis. So they want us to, we have to analyze this and come up with a solution that we're pretty darn sure that's going to work, because this has already been molded and made. And we want to find the cheapest, or I should say the most inexpensive way to fix this design flaw. So you see, injector breakaway head, that's the actual part that we need to modify, and that is the only part you are to modify. If you really want to change the whole design, you could go ahead, but remember, this is a fictitious design. It's not the original one, so it's not real. It doesn't work like the real part would. So I don't want you really tampering with that. And that's when you go into industry, you have to know to do that too. You don't want to change a customer's entire design. Right? You'll get in trouble for that, unless you have to. I mean, if there's really no other way around it, but you have to do some convincing of that, okay? You have to prove out that their design isn't going to work. All right, but anyway, we'll grab the whole E3 FEA. You can just double click on it. It should launch inside SolidWorks here. And let's see, any changes, just go ahead and hit OK. And I'm using SolidWorks 2020, by the way. All right, so here we have, you see it says twist before injection. So this thing twists, but this isn't the part we're editing. But let's go up here and let's do a cross section and see what's going on the inside. All right, as we do cross section, here we could actually see this is the breakaway head. See how this gets really thin here? That's the intent. The design intent is so that severs and breaks. And then the fluid is in here, and it just makes its way through. It's able to actually get through the needle and into the recipient. All right, now it can't fail. And what was happening is that this head here, even though clearance was designed in or what they thought was clearance, it was actually twisting or something was happening where maybe it moved forward and basically it closed off the whole area. Okay, so it couldn't actually make it through. So I'm going to cancel out of there. So what we can do is we'll hide this. We'll just click on this and hide it. And here you could see there's the actual needle and here's this part. Later on we could test it if we want. But we saw we have a very limited area inside there to work with. And we only want, like I said, you want to try and save money. So let's just figure on fixing this part right here. So let's open that up. Let's right click on it, open. All right, now I've already put in some features. I did cuts right here. And the very first exercise in the book, which I don't usually go through, I'll let you look at it. It's a split face. And it shows you how to make split faces. And the reason I made split faces here and here is so that you can simulate the twisting effect. Imagine if your finger and your thumb, like your finger went right here and your thumb went here, you could actually twist it. See the arrows? Those arrows are put in there specifically for this lesson. So in real life, those wouldn't be there. Just be aware. I just put those in so I could explain it better. So that gets twisted off. But let's try and simulate this. Now remember, we're using the low-level simulation, the free one that comes in every license. All right, so go to SolidWorks add-ins and make sure SolidWorks simulation is turned off. All right, if it's not there, that's good. Okay, that's fine. Now what you want to do is you want to go to Evaluate and find the Simulation Express Analysis Wizard. Select it. Now, over here, see Options, click on Options, make sure it's set to SI and hit OK. Down below, we're going to go ahead, we want to see megapascals, as we did before, so make sure it's set to mmgs. Sometimes I actually go back to Options. It's weird if you don't. I've seen it come up in PSI, and I don't want PSI in your results. If you give it to me in PSI, I'm going to send it back to you. All right, so hit Next. And so we can see here the material is already selected, but we'll find out what that is. I'm not sure what that was in there. Actually, it says it's not specified here, but we'll see what's going on. All right, so let's first of all add a fixture. Now the fixtures, we could actually make the base here the fixture. So select this face right here. That's what we're considering the immovable object. It could be this too. Either way is fine. But we want to really see this get severed. So let's go ahead and hit the green check so that there we have our fixed face. Now we'll hit Next. Now we have add force and pressure. Now you're probably thinking like, hey, wait, this is a torque analysis. Some of you might realize that. It is technically a torque analysis, and we will revisit this in a few weeks using the actual torque tools. One reason I have this is just to show we're going to use the low-level version here, and we're going to apply force on both of those faces that I broke. And we'll get somewhat of an effect of torque here. And I've run it through both, and it actually comes up pretty darn accurate. So go to Add Force. And instead of SI, newtons, change it to English IPS. Set it to, we're going to figure that, usually I put it in the case study. So let's go ahead and put in 20 pounds of force. And now select this little face here, rotate around, and select that little face there. And look at that. See the arrows? The direction? So the idea is it's like twisting on those faces. So just like a knob on a washing machine or a knob on a stove, you're turning it, okay? And the goal is it's going to sever that thin area and break it so that the fluid can flow out. Hit the green check. Let's go ahead and hit Next. Now, it is already set to acrylic. You know, I'm going to hit Change Material just to make sure. This might be an older material that no longer exists. I'm not sure. But let's go over here and hit the little arrow, find plastics, and we're going to go with acrylic. And just to show you here, the acrylic, we see the yield is at 45. If you change this to megapascals or MPa, there it is. 45 is our yield strength. So at that point, it's not necessarily breaking. It could be getting really close there. Tensile is actually up to 73. That's technically where we would probably be seeing the actual fracture occur. But yield at 45. Let's hit Apply and Close. Now it does turn it to transparency, which is kind of helpful. You could actually see the cutout there and how thin it gets. So the idea was designed to actually sever that area. We could leave it clear, but if you don't like it transparent like that, you could right click and go to change transparency and turn it off, or select a different material from the list for the appearance, okay, which won't override the actual acrylic material that we selected. But we could probably leave it like this and it's fine. Now you'll also see some other features that, like threads, take up a tremendous amount of resources on a computer. You might want to right click on those and suppress those, okay. Also these, if you can't select the surface, shift on your keyboard. Holding shift will allow you to select the outer surfaces here. It's not working for me, why not? Oh, there's a control. Nope. Okay, never mind that. Let's cancel that. All right, we should be okay leaving those in. But in real life, you might want to take them off. We could probably find them on the tree and suppress them, but I know it works with them on there, so it doesn't really matter. All right. So let's go ahead and hit next. And now the only option is run. So hit run simulation. Now it's going to break this down into a collection of triangles. Now this is where it looks a little strange. You see the exaggeration of it, what looks like stretching. Let's go ahead and hit yes, continue over here. Now we can see a factor of safety of 1. We can see the red is clearly there. All right. And the red tells us that that's beyond its yield, all right? But this is a binary, so it's like fail or not fail. So it's definitely failing. We don't know which area is failing first, but the one thing, the clue, as I've talked about before, is when you see the marbleized blue, that's usually pretty safe to say it's okay. Here we see red go all the way through. We can't really sever a cross-section, but you can see the red inside there as well. Okay, now let's go ahead and we're going to change it to stress, show von Mises. All right, or it's actually von Mises. I always, for some reason, call it von Mises. Now here we could see in megapascals, yield strength, because it's coming up as with the scientific notation, it's 4.5, but remember it's really 45. So right here is where we're experiencing. So anything above the blue is hitting yield, right, going past it. And what we saw was the tensile strength. We could use that to our advantage too. Tensile, remember, was 71, I believe. And so 71 is right about here. So anything above that is fracturing. And so we could see the red, that would be the first area. So we're good to go. It actually is failing and breaking off. So we want to make sure that part is functional. 20 pounds might be a bit excessive too. We might actually only want to do 10 now that I think about it. I might have put the wrong one in there. 20 pounds of force. But we're getting the results that we're hoping for. We don't see any red up at the top. We just see it around that area. So that's good. Okay, show displacement. We learned about this and basically how much is it moving by. And we can see metric here. Move the decimal place. We're moving about, let's see, -1. So that would be, it's moving less than a millimeter according to that. But anyhow, this one's kind of awkward because we're not truly using the torque analysis. What we're interested in though is this severing. Okay, so now that we have that, we could actually start taking some images of this. Let's go back to show factor of safety, and we can now take a picture of that. Let's zoom up on it. And sometimes, see this little box up here? Sometimes I like to have this close in proximity to it, because this is kind of the evidence that just so you have a backup of what's going on, like what the factor of safety is. Because if you just sever out the images and crop them, you don't know. So while we have that close in proximity, I just dragged it over. It's a little tricky to drag, but now you could hit Alt print screen. And let's go to our Word document that we opened up earlier. And let's zoom out here a little bit. Let's go to 100%. We'll get rid of that image soon here. And first one here, let's see, do we have a factor of safety in here? I actually don't. So we'll make this first one here. Steering wheel. Actually, it's not the steering wheel, of course. This is the injector break away. And we'll put in FOS, factor of safety 1. Let's put in a little dash there. Oops. All right, and just make sure you put in the date. All right, now the result, the injector cap appears to break within our yield limit. Okay, so now that we have that, oh, and actually, you know what? This is, we need to actually test it with the modification. So we really don't need this just yet. Let's go back down here, go to model, right? At least we have it set up so we could rerun it once we make the change. Now here's the thing. You can make a sketch pad and come up with some hand sketches on what you want to do as far as different concepts. I've seen probably a dozen different concepts over the years teaching this on how to correct this design to where we don't want this cap flying off, okay, easily or getting lodged into that area like we saw earlier in the assembly. So we need some way to hold it down or keep it away from there. Now what I've had is I've had students go in here and they draw little bosses, and so that it can't go too far away. But when they take the measurements, I've seen students not measure correctly when you go to the assembly. So like what I mean by this is, let's go back over here and let's bring in the nozzle, show it. Let's go to section. Okay, so I've had students right here put in little posts and then they leave a very small amount. So, but the problem is if you measure this, there's like very little room in there to begin with. Remember, this is really a small part. So to measure it, you go to evaluate and you go to measure, see the little tape measure, and click from here to here. And what we see, it's 60 thousandths of an inch. And I've seen people put in 30 thousandths nubs like right in here. Let's see if we use the markup tool. Maybe we could use that. Oh, markup's not available right now. Oh, there it goes. So kind of seen like little nubs drawn in like here, sometimes 4, sometimes 2, so it could teeter-totter, which really isn't a bad concept. And then they keep it at about, you know, the distance between that is 0.03, because remember it's 60 thousandths, so they're getting a little bit of clearance. So when this moves forward, pushes, it doesn't seal off this head. Okay, and remember, you're not supposed to modify this or the needle. I've had students ask, nope, nope, nope. If you really like have read through this and you're like, can I redesign it just for fun? You know, if you're into that, absolutely, let me know ahead of time, and I'll accept it, because otherwise I need you to focus on this. All right. So anyways, with that in mind, now I've also seen students cut out this segment right here, so fluid could flow through, because remember, we're trying to get the fluid to get through here and around and into the needle and as fast as possible. This is a rapid deployment. Okay, 30 thousandths of an inch isn't exactly a big thing, although needles are very thin, so it's not that big of a deal. All right, so there's a couple scenarios. Now, here's what we ended up doing where I worked. We ended up, to make sure, because basically, were we positive if we put those nubs in or those? Believe me, we thought about those ideas, but none of them felt comfortable, okay, putting them in. And you could try those. By all means, feel free to put those in. And you don't have to do much more analysis because that's not going to affect it. And we're not doing a fluid analysis of this, fluid analysis of this either, which actually would be really cool. It's just a little bit higher level than I want to take this class. But what we ended up doing was putting a tether. Now, a definition of a tether, when you hold a balloon that has helium in it, it rises in the air. There's a string attached to it. That's basically a tether. And so by modeling in this like little area here, making a tether, making it thin enough. When it's thin enough, remember, when plastics are thin, they bend a little bit easier versus when they're thicker and bulkier. So the theory was that the tether would, even though this gets twisted off, the tether would maintain its shape. All right. And you have to make sure it's small enough to fit in this area. But the nice thing about the tether, just on one side now, I've had people do tethers on both, and I'm like, well, then it's not going to really move much. It might actually hold it too close, okay? But one tether is what we ended up going with. And so it kind of like the whole thing tilts and rotates a little bit, and all the fluid makes its way through. And without actually having to really test it in the field, we were able to just come up with that idea, and it worked. So it's up to you. There's 3 different ideas right there. There's other ideas I've seen, but and here, let me show you how you would fix that, how you would model that up. So let's go back to the part. Turn off markup. Okay, so Control Tab. So for those of you who wanted to make the cutout, I've seen students do this where they select this face or this face and they draw in a little box. So like right here, actually, this is what I see most students do. They create a sketch on the side here. And if you want, you could actually use, this is kind of a neat little tool. You could do something like that. And then features, extrude cut, through all. Now, here's the problem, what I've seen students run into with that cutout. When they apply the force to these ends, there's so much red here, it might actually be snapping this off versus snapping the neck. So be careful of that if you make it too big. I've seen students make it really big, and I call them rabbit ears almost. They get so big. I've had students make big cutouts like, no, I want to make sure that fluid flows through there, which is good, but you got to be careful because it might fracture, break this, or bend it. It might make it too soft where it just bends and doesn't sever the cap. So be careful of this design. This is not, to me, an acceptable design. If you want to try it, by all means, I'm not going to be critical. I'll let you know what we experienced when we did analysis, or I'll give you my thoughts. But anyhow, let's look at another one. The other one is this, where students select this face, and they go and they put like little bosses. And remember, we have 60 thousandths of room. So you like 0.03 still gives it up 0.03 IN for inches. Wow, that seems actually quite large. That can't be right. I must have mismeasured something. But anyhow, just be aware that that one isn't, I'm not comfortable at all with that one. It just doesn't seem like it makes sense to me. But when you give me your designs, by the way, I'm looking more for your report. Well, you know, sell me on your idea. Sell me on the concept. And also, I'm looking at the quality of your report. Not particularly looking at, looking at the design, and I'll tell you some things, but I don't necessarily grade on this one, on the design, because you're still learning. I want you to try different things. I will write down where there's error, but, or where, you know, maybe you could thought, you know, maybe to help you, give you a second pair of eyes, you might say, like, you know, Joe, that might not work. But I'm not going to be critical as far as grading on it. Just make sure you make a good report. So anyhow, once you do make these changes. Now, let me show you the last one. What I ended up doing, this is what we did at the company I worked at. Went with the right plane here, started to sketch. I'm going to go to the right view orientation. And it was just this. We took the spline tool, dig it in, and have it come through. And again, you want to make sure, you can verify it later on. go to extrude, select that geometry, and we're going to make it we're metric here, but that's okay. We'll do a conversion. So put in 0.01 IN, so it converts it. So 0.254 millimeters. And over here for the thin feature, you'll see that's going to add thickness to that. So we could go ahead and put in the same 0.0 or 0.254. And now we can see a little tether. We might actually want to make it a little thinner. And also let's have it go mid-plane so it's centered. We'll try that. Actually, that might work. Now we could go ahead and rerun the analysis. So we go down here. Once you have this, actually go back to Evaluate, Simulation Analysis, and go to Next. It should still all be set up. Let's see here. Loads. It didn't remember, so let's go to Add Force. There. And there. And we had it. Let's change to English. And let's actually go with 10. I think it's supposed to be like more like 10 pounds. Hit the green check. The fixtures, let's add the fixture. Again, select that face there. Hit next. Next. Acrylic. I don't trust that one. I'm going to hit change. And again, let's pick that out. That's under plastics. Go with acrylic, apply, close, next, and run it. Hit yes. All right, look at that. And this is what's really cool. Look at how it's all bright red in there. We know that's where failure is occurring. Look at this, like no red, because it's so thin. So what you would do with this, get a good picture of it, Alt Print Screen, and start dropping these in. So this is the factor safety. Let's delete that. We could leave that in actually. Control V, put this in like so. You could rearrange the arrow if you want to do something like that to show the rotation. And in this case, we put in 10. And fixed, this base is fixed here. And then the torque, we could put like here. All right, so 10 pounds on there. So you could read that. Remember, there's the ability to crop. You go to Format and Crop. You can crop off this excess. And I should have done this before I put in all that fancy stuff. Okay, let's click, make it bigger. Let's move that around. And this is still valid right there. That's fixed. Okay, so we have that, and you'd want to go through and fix this. By the way, if you don't fix this, I will mark off on it. All right, so just be aware. If you forget to change these, it's gonna be marked as wrong. And so, like here, you know, this 20. Make sure you change that. Put in any changes, like the yield strength of the acrylic. Remember, it's 45. It says 60, so don't forget. All those things need to be updated, and so on and so forth. Then you'd put the other images in here, and that would be it. Now, again, you all know from the previous ones, make sure you get a good picture to drop in here. Delete these, change the company name, all that stuff, so it's all valid. And when you send me that report, that's what I'm going to be looking at. And you know, you can keep the explanation simple. You don't have to go into great detail. Just a sentence or two. Okay, and that concludes Lab 2.